Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, this is Mr. T with a tutorial today on solving optimization problems using calculus. And we'll be using derivatives to find the relative max and mins of problems to solve our problems. In each problem, we're going to follow a fairly straightforward and simple procedure. We will have to write some kind of function for whatever the problem is asking us to optimize. So you'll be seeing that as we go through. Many times this optimization function will have more than one variable, and if so, we will need a set of constraints or facts about the problem that relate the various variables together. That will allow us to use substitution into the optimization function because we want to turn the optimization function into having only one variable. That way we can take derivatives without having to use implicit differentiation or other kind of techniques like that. Once we have our optimization function, we will take the first derivative of that function with respect to whatever this variable is, and we will find our critical values. Remember, critical values are numbers that make the first derivative either equal to 0 or undefined. And we'll analyze those by organizing those on a number line to find the increasing and decreasing patterns for the function so that we can identify any relative max or mins for the problem. We'll select the appropriate critical value depending on the way the problem is worded and answer our problem. So today in this tutorial, I'm going to look at 5 examples, so the tutorial might be a bit lengthy. So I've shown here the order of the problems that we're going to look at. If you're interested in one of these particular problems, you'll be able to fast forward to that part of the tutorial. So let's get started with our first problem. Here we're looking for a pair of non-negative numbers that have a product of 96. So I'm going to use x and y to represent my two numbers. So our constraint here is that x times y equals 196. And our optimization function, we are trying to minimize a sum. So I'm going to use the letter S for sum. And we're trying to minimize 4 times the first number. So we'll let x be the first number. So 4x and plus the second number. So this is our optimization equation. Now we've got two variables here. So we're going to solve the constraint equation for one of the letters. So let's solve it for y. So we get y equals 196 over x. And we're going to substitute that amount into our other equation here to create a version of the sum equation with only one letter. And since we're going to be taking a derivative, I'm going to rewrite this equation here and move the x to the top. So now we want to find our derivative of s prime using our basic derivative rule. So we've got 4 and then the power rule here, 196 x to the negative 2. Now I'm going to factor out a x to the negative 2 and a 4. And we get 1 minus, I'm sorry, that's not going to be 1, that's going to be x squared minus 49. And I'm going to rewrite that without the negative exponents. And now we can find our critical values. Now this is our s prime. So we want to find values that make it equal to 0, which will mean setting the numerator equal to 0, and values that make it undefined, which would mean setting this equal to 0. So our critical values are plus and minus 7 and 0. Now we really can throw away 0 and negative 7 because in our problem we want to have non-negative numbers. So when I put these on the number line, I really don't need to look at these numbers over here because those are not part of our domain. So if we plug in, say, test point here, say 1 into our derivative, I'm going to have positive for the 4. This would become negative if I'm plugging in, again, positive 1. And our denominator is positive, so we are decreasing. And if we plug in, say, 10, I've got positive. This would be 100 minus 49 positive over positive, so we're positive, so we're increasing. So 7 gives us a relative min, and for our problem, we're looking for a min. So in our problem, x equals 7. So now we need to find y, so now we can substitute this into our equation over here. This is y equals. So y equals 196 over 7, which is 28. And so our two numbers were 7 and 28. So we're done with this problem. So let's go to problem 2. Okay, here we're creating some kind of box, and we start with a rectangular piece of cardboard. And we're told that it's 12 inches by 18 inches. And we're cutting squares out of each corner. And we're trying to find out what size those squares will be. So each one is the same size. And we're going to cut those out, and we're going to fold up those tabs. So I'm not going to, let's just quickly here, we're erasing, cutting out those corners. So you can see we've got these tabs. And we're going to fold them up, and we're going to create a box. So this dimension here, this 18 was the original dimension, and we've taken away x. So this dimension is 18 minus 2x. And on this side, this dimension here is going to be 12 minus 2x. So we're creating a box. Oops, let me start that over. That wasn't a very good box. So we have a box like this. And this again is 18 minus 2x. This is 12 minus 2x. And this height is x. And we're trying to maximize volume. So the volume of a box is those three things, those three dimensions multiplied together. So to make it easy for the derivative, we're just going to multiply that all together. And if we FOIL this and distribute the x, we get the volume is 216x minus minus 60x squared plus 4, that's x squared, plus 4x cubed. So that's our volume function. So now we want to take the derivative of that. So if we take the derivative of that, we get 216 minus 120x plus 12x squared. And now we want to set that equal to 0 to find our critical values. All those numbers are divisible by 12, so we can divide the entire equation by 12, and we end up with x squared minus 10x plus 18 equals 0. Now that's not factorable, so we could use the quadratic formula or a graphing calculator to find the zeros. I've already done that for you. Hopefully you know how to do that. So we get 2.35 if I round that, and 7.65 as our two values. Now we kind of could determine that this value is not going to be appropriate, because if we have 12 inches here and I cut 7.65 out of this corner and 7.65 out of this corner, that's more than 12 inches. So this one's really not even feasible. But I'll just go ahead and put it on the number line, but we should rule that out. We also do not need to look at negative values, because it would be impossible to cut out a negative number of inches. So if I put in 1 into my derivative equation here, if I put 1 into this, I get a positive number, so we are increasing. If I put, say, 5 into this and calculate, I get a negative number, so I'm decreasing. And if I put a big positive number in, this would become positive, so I'm increasing. But again, the most we could cut out would be 6 inches. Anything over 6, our side here would be a negative side. But we're looking for a max, and we have a max here. So our square that we want to cut out is 2.35 inches by 2.35 inches. If the problem had asked what is the max volume of the box, we could then plug this number into our volume equation here and calculate the volume. And in this particular case, that volume, which is the maximum volume, comes out to be 228.2 cubic inches. All right, let's proceed to example 3. Okay, here we have two shapes, a circle and a rectangle. And we're told on the rectangle that its length is twice the width. So if we use x here for the width, this is going to be 2x. And we have a circle with some unknown radius. And we are told that the combined perimeter, so the perimeter of the circle is the circumference, which is 2 pi r. And the perimeter of this box would be x, and x is 2x and 4x's, so 6x. And we're told that that is equal to 100 inches. And we are trying to minimize the total area. So the total area would be the area of the circle plus the area of the square, of the rectangle. And this is what we want to minimize. So again, we've got two variables. So I have to solve this equation for either x or r, and I'm going to solve it for x. It's going to be easier if we convert this pi to a decimal number. I mean, we could do it with exact solutions, but it's going to make our math easier if we go ahead and convert to decimal. And if I solve this for x, I'm going to subtract this and divide by 6, and I get the equation x equals 16.7 minus 1.05 r. Now we're going to substitute this in up here for here. So my revised area function is going to be this equation here. And we can take the derivative of this. We'll use the chain rule here, the generalized power rule. And I'm going to go ahead and also, I'm going to make that be decimal just to put everything in decimal here. So we get here 6.28 r. And now I've got to multiply the 2 times the 2 is 4. Our expression, and we're going to reduce the power by 1, so that becomes 1, and then the chain rule here, we take the derivative of what's inside, and we get negative 1.05. Now I'm going to multiply the 4 times the negative 1.05 and distribute that into the parentheses, and also then combine like terms. And if I simplify my derivative, I get this equation here, sorry for the mistake here. I get 10.69 r minus 70.14. So I just distributive property here, combined like terms, and now I need to find my critical value, so I'm going to set that equal to 0, and I get r equals 6.56. If we organize that on a number line, if I put 1 into here, I get a negative number. And if I put a big number for R, I'm going to get positive. So we can see here we're decreasing, increasing. So this number is in fact a min. So my radius is 6.56. I've got to put that number over here and calculate my x. And if I do that, I get x equals 9.81. So I have a circle of radius 6.56, and my rectangle dimensions would be 9.81 in this direction and twice that in this direction. So it would be 19.62 in this direction. All right, let's move on. Okay, here we have a problem that's asking what's the point on this parabola that's closest to the origin. I've already, on my graphing calculator, made a rough sketch of that. We get a parabola that's coming down something like that. And we are looking for the point on this parabola, some point xy, whose distance here to the origin, that distance is at a minimum. So if we use our distance formula, distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. So our distance here is the square root of x squared. And now we're going to replace y with this so we get one letter. Now we could take the derivative of this, but a simplification we can do on this is the values of x that minimize this function would be the same values of x that minimize d squared. So if we find the d squared, we square both sides, then we get this function. So it's going to make it easier to take our derivative. So we're going to take the derivative of d squared. And we get here 2x. And now I'm going to use our generalized power rule here to take the derivative of that. And now we've got to multiply by what's inside, derivative of what's inside, using the chain rule. And if I distribute here and expand and get like terms, our derivative function is 4x cubed minus 36x squared plus 114x minus 120. Now that's the derivative of d squared. And we want to find our critical values. Now this one, pretty much what we need to do is use a graphing calculator to find the zeros of this function. So offline I have done that, and there's only one x-intercept in this cubic function, and the x-intercept is at 2.26. Now we should just verify that indeed that gives us a relative min. So if I put a test point of 0 into this, I get negative 120, so I get a negative number. And if I put a big positive number in here, I'm going to get positive. So we do have decreasing, increasing. So 2.26 is a min. We verified that. So now we wanted to know the point that's closest. So to find the y value, we can just put 2.26 into our equation here. And if we do that, we get 1.55. So our point that's closest is 2.26 and 1.55. So that's the point on this parabola that's closest to the origin. All right, let's move on to our last problem. Okay, our final example here, example 5, we have a business problem, and we are producing and manufacturing and selling a product. and we are given what's called a demand function for the product. It relates the price of the product and the number of units to be sold. And we also are given the total cost of manufacturing X units of the product. And we're trying to find what price should we set so that we will maximize our profit. Now we need to remember a few basic definitions here. The revenue for producing a product is the price, which is our demand function, times the number of units. And also, since we're dealing with profit, profit is revenue minus cost. So for our function here, we've got X times our price minus our cost function, 50,000 plus $100 per unit. And we want to simplify that equation. We need to distribute the X here. And I'll put it as a fractional exponent since we're going to be taking derivatives. And we can combine our like terms here, and we've got a profit function of 900x minus x to the 3/2 minus 50,000. And we want to take our derivative here. So we get 90 minus 3/2 x to the 1/2. And we want to find our critical values, so we're going to solve that equal to 0. So we will move our x squared to the other side. We can multiply both sides by 2/3 to get rid of our fraction. X squared. I'm sorry, this is x to the 1/2. And to get rid of that exponent, we're going to square both sides. And we get x equals 360,000. So that's our number of units. Now let's verify that that indeed is a max or a min. And in this case, we're hoping it's a max. So if we put a small number into our derivative, if we put, say, 0 in here, we've got a positive number. And if I put a really big number, like 1 million or 2 million into here, we're going to end up with a negative number. So we do have increasing followed by decreasing. So we have a max. So we want to sell 360,000 units to maximize our profit, but we want to find price. So we need to put this back into our demand function. So we've got 1,000 minus the square root of 360,000, which is 1,000 minus 600, which is $400. So if we set our product at $400, we will maximize our profits. Set our price for our product. Okay, I hope this helps. We've been through 5 optimization problems, and good luck on your work.
Are you ready? Are you ready?